My dear participants, we shall continue on comparison of simulation based results. We are dealing with the exercises. So, we have already verified these things. See, exercise on simulation from chi-square distribution. Simulate 1000 of realizations from chi-square with 8 degrees of freedom and estimate mean and variance. Compare it with the theoretical result. Of course, mean is equal to 8 and variance is equal to, mean is equal to degree of freedom in chi-square random variable, and variance is twice of degree of freedom. So, variance should be 8. Now, see, verify these results on the simulated data. So, here I am going to just copy this command here. So, what should be the mean of this random variable? Its mean should be around 8, because these are the observations with degree of freedom 8, and chi-square distribution, mean of chi-square distribution is equal to degree of freedom. So, it should be around 8. See, it is 8.06, and its variance of x, it should be twice of 8, that is 16. So, it is 15.94. So, that means simulation supports this theoretical result. See here, exercise on simulation from binomial distribution. Simulate 1000 observations from binomial with size 10 and p is equal to 0.5. Compute its mean and variance and compare it with the true mean, that is 10 times 0.5. So, it should be 5, and variance 10 times 0.5 by 0.5. And then the next problem is make a histogram of the simulated observations and add a normal curve with mean is equal to 5 and SD is equal to, variance is equal to 2.5 on it. Then comment on the closeness of the histogram and normal curve. Do you feel that binomial probability can be approximated by a normal probability? So, here we shall simulate so x is the random variable which is generated from binomial distribution with size equal to 10. Now, what should be the mean? Mean should be, mean is nothing but actually mean of binomial parameter is equal to 10 into 0.5. So, it should be around 5, and see what mean you get. Mean of x, it should be around 5. So, it is 4.97. So, that means simulation results matches with the exact result. Even if you increase the size of simulation here somewhat, instead of 1000, if we are generating 10,000, then get the mean of, it is 5.01. So, it gets closer and closer. So, it is exactly. And what is the variance? The variance is nothing but 10 into 0.5 into 0.5. So, variance should be 2.5. So, here we can make a histogram and hist of x and prob is equal to true. So this is the histogram. This is the histogram we have got. This is the histogram. And now we can add a normal curve on this, and that is d, that is the function curve d norm x mean is equal to 5 and SD is equal to SQRT 2.5. Actually mean is equal to this and SD is equal to 2.5, and add is equal to true. Actually, we have to add a chunk here. It is better that I should add a chunk here. Control plus Alt plus I, and here I should issue the command, that is x is equal to control plus enter, R binom, and then hist of x prob is equal to true, and then we are going to add a curve and here d norm x mean is equal to 2.5, mean is equal to not 2.5, mean is equal to 5, comma SD is equal to 2.5, and then add is equal to true, and then we run. See, we run the whole chunk. See, both the distributions are matching. And that's why we can approximate. See, to some extent they are matching. So that means we can approximate this. See, comment on the closeness of histogram and normal curve. Do you feel that here SD is equal to SQRT square root of 2.5? Then this will be the exact situation. Now we should run. Yes. Now see this histogram, and they are not in very close agreement because it is somewhat left skewed distribution. And but there is some closeness between the two. So this is the this is nothing but the central limit theorem. Central limit theorem says that if we increase the size here, say 10,000, situation will be better. So this is all about the closeness of normal and binomial distribution. Now I am going to talk about quantile plots. See, quantile plots known as QQ plot are a type of scatter plot used to compare distributions of two groups or to compare a sample with a reference distribution. The line y is equal to x implies both are same. So here the R function QQ plot is meant for graphic comparison of the two data sets or one data with the reference distribution. So here we are simulating compare two standard normal. So x is equal to R norm, it is standard normal. A is equal to R norm, so it is also 1000 observations from the standard normal, and then we are partitioning O par, means we are partitioning the screen between, and par MF row is equal to 2 by 2, 2 rows and 2 columns, and then we are making a graph of QQ plot XA, and then we are simulating another set of observations, and that is 1000 observations with mean is equal to 3, SD is equal to 2, and then we are making a QQ plot XB. X is from normal 0, 1 and B is from normal with mean 3 and SD 2. And then we are simulating 1000 observations from T distribution with degree of freedom 2. And then we are making X versus, so this is the third graph, C X versus C1. So, and then D R E X, see here EXP R norm, so that is simulation from log normal distribution, and we are comparing this with normal distribution. And then par O par means we are returning, because we have made here O par is equal to par graphic parameter, and that is MF row. That means we are partitioning the screen in 2 rows and 2 columns, because we need to generate 4 figures, and those figures have been generated here. So if we run, see what happens. See, this is the result. This is the result. So here on x and y axis both are the same, both are the from normal distribution. So y is equal to x is satisfied. Here in the case of B, B is what? B is nothing but actually B is nothing but normal distribution with mean is equal to 3, SD is equal to 2. So SD is equal to 2. So here it is again satisfied, but C1 has heavier tails. C1 is from T distribution, C1 is from T distribution with degree of freedom 2. So it has heavier tails. So in the tails they are differing. In the tails they are differing. And C, D is left skewed distribution. So it is not satisfying y is equal to, because on x axis it is standard normal, and on y axis it is the log normal distribution, and that's why it is not satisfying y is equal to x. So y is equal to x is getting fully satisfied here, because on x axis it is normal, standard normal, on a axis also standard normal. Here also they are to some extent satisfied, because only change of location but trend is same. Here C1 has T distribution with C1 on y-axis we are having T distribution with 2 degrees of freedom which has heavier tails. So, in the tails they are differing. And here actually on D we have log normal distribution, and on x-axis we have a standard normal, so they are not matching. Note that in the last two figures, distributions are not matching and the line y is equal to x is not satisfied. Moreover, if you want to compare two real data vectors x and y, they can be compared in the same manner. So, suppose we have a data x and y, we can have QQ plot x comma y and we can get the output. Exercise: compare the distribution of height and weight. Acha, no. Normal probability plot, QQ norm. The function QQ norm compares normal distribution with the data set, because normally in statistical theory we talk of assumption of normality, like in the case of linear models and in the case of design of experiments, mostly we assume that error follow normal distribution. So, we have to check that normality, and for that here QQ norm is the function. So, what we are doing? We are first making O par MF row. So, it is one row and two columns. We are partitioning the screen into one row and two columns. Then we are simulating 1000 observations from normal 0, 1. Then we are having QQ norm. So, it will generate a plot, and then we are having QQ line x. So, this will be in the first graph, and in the second panel x is equal to REXP, 1000 rate is equal to 800, QQ norm, then QQ line. So, when we will generate these, see normal QQ plot. So, here theoretical quantiles and sample quantiles, both are same, and that is why they are matching. Here on sample quantiles, they are from exponential distribution. So, here theoretical quantiles are from normal distribution. So, they are not matching, and that is why y is equal to x is not. It should go on, it should be like here, and line should like here, line matches with the trend. So, here that matching is not satisfied, and here see, note that data xc which follows exponential distribution is not matching with the normal distribution. This is evidenced from the fact that in case of exponential, reference line is not matching the plot with the plot. Reference line is not matching with the plot. So, this is the conclusion on the basis of QQ plot. Using lattice package, we shall make use of density plot and QQ math. Actually, lattice package, so far we have been talking about base graphics. Base graphics were developed by Dipayan Sarkar, and his PhD student base graphics were developed by Robert Gentleman, one of the two R developers. And his PhD student, Robert Gentleman's PhD student, Dipayan Sarkar, an Indian, he developed a lattice package. Lattice package is meant for multivariate graphics, and only after the introduction of lattice package, scientists got attracted towards use of R, because they were having very nice graphics and they were having a lot of graphic facilities. So, this is a great contribution due to an Indian, and he is Dipayan Sarkar. And this lattice package is the part of core distribution of R, that is the part of base distribution of R. And when you download R, it only out of 21,000 packages, only around 25 packages are in the base, and lattice is one among them. So here to plot a density we use the formula argument, that is density plot. There in base R it is density, but in lattice package it is density plot. So R norm. So when we run this, R norm and density plot, we have to require lattice and then R norm and then density plot. See, this is the density plot, density, and this is the density plot of normal distribution, and these are the observations shown in the density plot. These are the simulated observations. Similarly, to run R gamma, see. So here these are the gamma observations from gamma random variable, 10,000 observations, and shape is equal to 1.2, rate is equal to 0.02, and then we are defining density plot. The function is not density, it is density plot, and that is we are using the formula argument. We use this tilde means formula argument with x. So we are getting density plot. This is the density plot based on these observations which were simulated from gamma distribution. Density plot from Weibull. See, we are simulating 5,000 observations with shape is equal to 1.5, scale is equal to 50. Then we are making a histogram, and then we are making a density plot also. See, this is the histogram on the basis of simulated data. So here the function in base package is hist, but here the function is histogram, and we use the formula argument tilde. So this, and then we are getting density plot tilde y, and this is the non-parametric density estimator and its plot on the basis of the function, and that is density plot. Then QQ math, we have already talked about QQ plot. QQ plot is in the base package, but in lattice it is QQ math. So we are simulating 5,000 observations with shape is equal to from Weibull distribution with shape is equal to 1.2 and scale is equal to 50. So if we run this, see, if we write QQ math, so here it compares, simulated data is from Weibull, but it compares with the normal distribution and see what shape you get. See, it is not y is equal to x, because on x axis it is q norm. These are the observations from normal distribution, and on y axis they are the observations from Weibull distribution. So since both are not matching, it is this kind of curve comes. See, if we write here QQ math y tilde distribution, so here we can define a distribution. QQ math has the facility. Distribution is equal to function of p, q Weibull, quantiles of Weibull. So, and p and then shape is equal to 1.2 and scale is equal to 50, from which we are. So on x axis actually we are defining the same distribution, reference distribution from which data is being simulated. And see, if we run this, what we get? See, here exactly y is equal to q we are getting. So that means if we have the same distribution on y axis simulated data from the, because these here distribution is also viable distribution, or simulated data is also from viable. So that's why y is equal to x is getting satisfied. And there are some very powerful functions on QQ math. So to display some examples, require lattice and help pack is equal to lattice. See, trellis graphics for R, and here we can go for QQ math. So we can go for QQ math. QQ math. Yes, QQ math. So here QQ math, and these are the details of QQ math. And here we have a data. See, we can run this data. See, here first we should understand the data. These are the heights of the singers of base 2, base 1, tenor 2, tenor 3. So these are the heights of the singers, and they are, first I would like to explain the data. The data is equal to singer. So help singer. See, heights of New York Choral Society singers. Description: heights in inches of the singers in the New York Choral Society in 1979. The data are grouped according to the voice part. So those are voice part. The vocal range for each voice part increases in pitch according to the following order: bass 2, bass 1, tenor 2, tenor 1, alto 2, alto 1, and then soprano 2 and soprano 1. So these are the levels. So when we run this graph, actually it is being separated by these categories, and for each category here this is the QQ plot and QQ line. So bass 2 it fits good, but slope is somewhat sharper. Then here also fits good, but here also, but here it is y is equal to x exactly. So here somewhat. So this is the plot of the data. So QQ norm has the capacity to analyze these data sets.